Well, welcome back to our course on computer organization and architecture. We're continuing in our third part of our course where we're focusing on arithmetic and logic operations. We talked about number systems, computer arithmetic, and now we're going to get into logic systems in this lecture. So let's go ahead and do an overview of the things that we'll cover, and then we'll come back to and give a quick reminder of the things that we have covered. So digital logic is the topic, and if you've never heard of Boolean algebra, you'll get a chance to get exposed to it today. Also, another way to be thinking about it is if you took discrete mathematics, this will be something that will be a little bit familiar to you, but in a different context. We'll talk about gates. This is how the digital logic is conceived when you're talking about computers and various type of digital electronics. Then we'll get into combinational circuits, which how we go about doing the implementation of Boolean functions. We'll talk about multiplexers, decoders, read-only memory, adders. These to read-only memory is probably something that you remember that we talked about earlier. So that's combinational circuits, and we'll talk about sequential circuits, flip-flops, registers, and counters. And then finally, we'll talk about programmable logic devices, PLAs, programmable logic arrays, and field programmable gate arrays. So let's go ahead and get into the material here. So the digital circuitry in digital computers and other digital systems is designed, and its behavior is analyzed with the use of mathematical discipline known as Boolean algebra. The name is in honor of an English mathematician, George Boole, who proposed the basic principles of this algebra in 1854 in his treatise, An Investigation of the Laws of Thought, on which to found the mathematical theories of logic and probabilities. 1938, Claude Shannon, a research assistant in the electrical engineering department at MIT, suggested that Boolean algebra could be used to solve problems in relay switching circuit design. Shannon's techniques were subsequently used in the analysis and design of the electronic digital circuits. Boolean algebra turns out to be a convenient tool in two areas. First, in terms of analysis, it's an economical way of describing the function of digital circuits. And in terms of design, given a desired function, Boolean algebra can be applied to develop a simplified implementation of that function. Can be helpful for visualizing Boolean algebra operations to illustrate corresponding operations on sets. So we'll get a chance to see that with this table here. We can define a set as a collection of elements S together with a rule that determines what elements belong to S. For example, the set of positive integers less than 5 is 1, 2, 3, 4. Logic operations can be performed on sets in much the same way as on Boolean variables. Corresponding to the basic Boolean operations of and, or, and not are the logical sets and operations of intersection, unions, and complement. These are shown in table 12.2 that we have here on the display now. The intersection of two sets A and B is a set of all elements that belong to both A and B. This operation is designated with the operator an inverted U. For example, if A is the set of positive integers less than 5 and B is a set of even positive integers less than 10, then the union of A and B is equal to 2 and 4. The intersection corresponds to the Boolean operator and. The union of two sets A and B is a set of all the elements that belong to A or B or both. The operation is designated with the operator U for A and B defined in the preceding paragraph. A union B is 1, 2, 3, 4, 6, 8. Union corresponds to the Boolean operator OR. Complement of set A depends on the context. Generally, attention is confined to the subset of some given set X, which is considered as a universal set for this context. The complement of a set S designated by S consists of all the elements in the universal set not found in S. For example, if X is the set of all positive integers, and for A and B defined above, A is a set of all integers greater than 4, B is a set consisting of all odd positive integers plus all even integers greater than 9. Complement corresponds to the Boolean operator not. As with any algebra, Boolean algebra makes use of variables and operations. In this case, the variables and operations are logical variables and operations. Thus, a variable may take on the value 1, which is true, or 0, which is false. The basic logical operations are and, or, and not, which are symbolically represented by dot, plus sign, and overbar. So keep that in mind, hopefully over a period of time, you'll get familiar with this notation. The operation and yields true, that is binary value 1, if and only if both of its operands are true, both of its inputs. The operator or yields true if either or both of its operands or inputs are true. The unary operation not inverts the value of its operand, of its input. In the absence of parentheses, the and operation takes precedent over the or operation. Also, when no ambiguity will occur, the and operation is represented by simply concatenating instead of the dot operator. Table 12.1a defines the basic logical operations in the form known as a truth table, which lists the value of an operator for every possible combination of values of operands. The table also lists 3 other useful operators, XOR, NAND, and NOR. The exclusive OR XOR of 2 logical operands is 1 if and only if exactly one of the operands has the value 1. The NAND function is the complement that is not of the AND function, and the NOR is the complement of OR. As we shall see, these 3 new operations can be useful in implementing certain digital circuits. The logical operations, with the exception of not, can be generalized to more than 2 variables as shown in table 12.1b. With these definitions in mind, we can visualize the Boolean operators defined in table 12.1a. Figure 12.1 is where we see how that actually starts to come out. The Boolean variables are represented by circles, which can be viewed as sets depicted in Venn diagrams. From the perspective of the Boolean algebra, the surrounding rectangle, including the circle, represents all possible combinations of values of A and B. From a set perspective, the surrounding rectangle represents the universal set. Figure 12.2 depicts the Venn diagram corresponding to 3 Boolean variables. The 3-bit numbers give the Boolean value for A, B, and C in the different regions. Now here in table 12.3, it summarizes key identities of the Boolean algebra. The equations have been arranged in 2 columns to show the complementary or dual nature of and or operations. There are 2 classes of identities, basic rules or postulates, which are stated without proof, and other identities that can be derived from the basic postulates. The postulates define the way in which Boolean expressions are interpreted. One of the 2 distributed laws is worth noting because it differs from what we would find in ordinary algebra. So, A plus the quantity of B times C is equal to the quantity of A plus B times the quantity A plus C. The 2 bottom expressions are referred to as De Morgan's theorem. We can restate them as A nor B is equal to not A and B, and A NAND B is equal to not A or B. The reader is invited to verify the expressions in table 12.3 by substituting actual values, that is the ones and zeros, for the variables A, B, and C. So anyway, those are some useful things that you can make sure that you keep in mind. Now we get a chance to look at the basic logic gates. The fundamental building block of all digital logic circuits is the gate. Logical functions are implemented by the interconnections of gates. A gate is an electronic circuit that produces an output signal that is a simple Boolean operation on its input signals. The basic gates used in digital logic are AND, OR, NOT, NAND, OR, and XOR. Figure 12.3 depicts these 6 gates. Each gate is defined in 3 ways. First, the graphical symbol, the algebraic notation, and the truth table. The symbology used in this chapter is from the IEEE standard 91. Note that the inversion not operation is indicated by a circle. Each gate shown in figure 12.3 has one or two inputs and one output. However, as indicated in table 12.1b, all of the gates except NOT can have more than 2 inputs. Thus, X plus Y plus Z can be implemented with a single OR gate and 3 inputs. When one or more of the values at the input are changed, the correct output signal appears almost instantaneously, delayed only by the propagation time of signals through the gate, which is known as the gate delay. The significance of this delay is discussed in 12.3, so keep that in mind when we start to talk about flip-flops. A little bit of a hint there. In some cases, a gate is implemented with 2 outputs, one output being the negation of the other output. Here we induce a common term. We say that to assert a signal is to cause a signal line to make a transition from its logically false, that is 0 state, to its logically true, that is 1 state. The true, that is 1 state, is either a high or low voltage state depending on the type of electronic circuitry. Typically, not all gates types are used in implementation. Design and fabrication are simpler if only 1 or 2 types of gates are used. Thus, it's important to identify functionally complete sets of gates. This means that a Boolean function can be implemented using only the gates in the set. The following are functionally complete set. First, AND, OR, and NOT. Second, AND and NOT. Third, OR and NOT. Fourth, NAND. And fifth, NOR. It should be clear that the AND, OR, and NOT gates constitute a functionally complete set because they represent the 3 operations of the Boolean algebra. For the AND and NOT gates to form a functionally complete set, there must be a way to synthesize the OR operation from the AND the NOT operations. And so we're not going through the details for each of those cases, but that's true for each one of these scenarios. Similarly, the OR and NOT operations are functionally complete because they can be used to synthesize the AND operation. Figure 12.4 shows how the AND, OR, and NOT functions can be implemented solely with the NAND gate. And what we're going to see is for the implementation of hardware, the easiest gate to manufacture is the NAND gate, so that's part of the motivation. Figure 12.5 show the same thing for NOR gates. For this reason, digital circuits can be and frequently are implemented solely with NAND gates or solely with NOR gates. You might remember NAND and NOR when we were talking about flash memory and some of the things that you can do with that. With gates, we have reached the most primitive circuit level of computer hardware. An examination of the transistor combinations used to construct gates departs from the realm and enters the realm of electrical engineering. So for those that are engineers, you might be interested in that, but others probably not. For our purposes, however, we will We are content to describe how gates can be used as building blocks to implement the essential logic circuits of a digital computer. So let's talk about a combinational circuit. Combinational circuit is an interconnection set of gates whose output at any time is a function only of the input at that time. As with a single gate, the appearance of the input is followed almost immediately by the appearance of the output with only gate delays. In general terms, a combinational circuit consists of n binary inputs and m binary outputs. As with a gate, a combinational circuit can be defined in three ways. First, truth table. For each of the 2 to the n possible combination of the input signals, the binary value of each of the m output signals is listed. Second, a graphical symbols, the interconnection layout of the gates is depicted. And third, Boolean equations. Each output signal is expressed as a Boolean function of its input signals. A Boolean function can be implemented in electronic form as a network of gates. For any given function, there are a number of alternative realizations. Consider the Boolean function represented by the truth table in table 12.4. That's what we're showing here on the screen now. There are 3 combinations of input values that cause f to be 1, and if any of these combinations occurs, the result is 1. This form of expression for self-evident reasons is known as the sum of products form. Figure 12.6 shows a straightforward implementation with and, or, and not gates. And so this is where we start to look at if we're going to create this kind of programming, if you will. This is what the outputs would look like. Another form can be derived from the truth table. The SOP form expresses that the output is 1 if and only if the input combinations that produce 1 is true. We can also say that the output is 1 if none of the input combinations that produce 0 is true. This is the product of sums, or POS form, which is illustrated in figure 12.7. So that's what we're showing on the display now. For clarity, not gates are not shown. Rather, it is assumed that each input signal and its complement are available. This simplifies the logic diagram and makes the inputs to the gates more readily apparent. So you just have the bar on top is the way we're showing it for the ones that are inverted. Thus, a Boolean function can be realized in either SOP or POS form. At this point, it would seem that the choice would depend on whether the truth table contains more 1s or 0s for the output function. The SOP has 1 term for each one, and the POS has 1 term for each 0. However, there are certain considerations. It's often possible to derive a simpler Boolean expression from the truth table than either the SOP or the POS. It may be preferable to implement the function with a single gate type that is a NAND or NOR. The significance of the first point is that with a simpler Boolean expression, fewer gates will be needed to implement the function. 3 methods that can be used to achieve simplification are algebraic simplification, Carnot maps, and Quinn-McCusley tables. And we'll get a chance to get more insight into that as we progress here. Algebraic simplification involves the application of the identities of table 12.3. So you might want to go back and review that for a second if you want to reduce the Boolean expressions to one with fewer elements. For example, consider again equations 12.1. This expression can be implemented as shown in figure 12.8, what we're showing here. The simplification of equation 12.1 was done essentially by observation. For more complex expressions, some more systematic approach is needed. For the purpose of simplification, the Carnot map is a convenient way of representing a Boolean function of small number up to 4 of variables that the map is an array of 2 to the n squares representing all possible combinations of values of n binary variables. Figure 12.9a, part of what we're showing here, shows the map of 4 squares for a function of 2 variables. It is essential for later purposes to list the combinations in the order 0, 0, 0, 1, 1, 1, and 1, 0, because the squares correspond to the combinations are to be used for recording information. The combinations are customarily written above the squares. In the case of 3 variables, the representation is an arrangement of 8 squares. Figure 12.9b shows this, with a value for one of the variables to the left, for the other 2 variables above the squares. For 4 variables, 16 squares are needed, with the figure arrangement indicated in figure 12.9c. So it's getting a little bit more complicated. The map can be used to represent any Boolean function in the following way. Each square corresponds to a unique product in the sum of products form, with a 1 value corresponding to the variable and a 0 value corresponding to the not of such variable. Thus, the product AB corresponds to the 4th square in figure 12.9a. For each such product in the function, 1 is placed in the corresponding square. Thus, for the 2 variable example, the map corresponds to AB plus AB. Given the truth table of the Boolean function, it is an easy matter to construct the map. For each combination of values of variables that produce a result of 1 in the truth table, fill in the corresponding square of the map with 1. Figure 12.9b shows the results for the truth table of table 12.4. To convert from a Boolean expression to a map, it is first necessary to put the expression into what is referred as the canonical form. Each term in the expression must contain each variable. So, for example, if we have equation 12.3, we must first expand it into the full form of equation 12.1 and then convert this into a map. The labeling used in figure 12.9d emphasizes the relationship between variables in the rows and columns of the map. Here, the 2 rows embraced by the symbol A are those in which the variable A has the value 1. The rows not embraced by the symbol A are those in which A is 0, similarly for B, C, and D. One of the map of a function is, once the map of a function is created, we can often write a simple algebraic expression for it by noting the arrangements of the ones on the map. The principle is as follows: any 2 squares that are adjacent differ only one of the variables. If 2 adjacent squares both have an entry of 1, then the corresponding product terms differ only one variable. In such a case, the 2 terms can be merged by eliminating that variable. For example, in figure 12.10a, the 2 adjacent squares corresponding to the 2 terms a, b, c, d and a, b, c, d. So that's what we're starting to see there. So a, b, c, d and a, b, the A, B, C, D and A, B, C inverted D. This process can be extended in several ways. First, the concept of adjacency can be extended to include wrapping around the edges of the map. Thus, the top square of a column is adjacent to the bottom square, and the leftmost square of a row is adjacent to the rightmost square. So maybe if you were to put this on a ball and it kind of fits just right, you can see how you're wrapping things around in 2 directions. These conditions are illustrated in figure 12.10b and c, still as a flat matrix there. Second, we can group not just 2 squares, but 2 to the n adjacent squares. that is 2, 4, 8, etc. The next three examples in figure 1210 show groupings of 4 squares. Note that in this case, 2 of the variables can be eliminated. The last 3 examples show groupings of 8 squares, which allow 3 variables to be eliminated. We can summarize the rules for simplification as follows. 1, among the marked squares, square with a 1, we find those which belong to a unique largest block of 1, 2, 4, or 8, and circle those blocks. Select additional blocks of marked squares that are as large as possible and as few in number as possible, but include every marked square at least once. The results may not be unique in some cases. For example, if a marked square combines with exactly 2 other squares and there is no 4th marked square to complete a larger group, then there is a choice to be made as to which of the 2 groupings to choose. When you are circling groups, you are allowed to use the same 1 value more than once. Continue to draw loops around single marked squares or pairs of adjacent marked squares or groups of 4, 8, or so on in such a way that every marked square belongs to at least 1 loop. Then use as few of these blocks as possible to include all marked squares. Figure 1211A, based on table 12.4, illustrates the simplification process. If any isolated ones remain after the groupings, then each of these is circled as a group of ones. Finally, before going from the map to a simplified Boolean expression, any group of ones that is completely overlapped by other groups can be eliminated. This is shown in figure 1211B. In this case, the horizontal group is redundant and may be ignored in creating the Boolean expression. Additional features of Carnot maps needs to be mentioned. In some cases, certain combinations of values of variables never occur, and therefore the corresponding outputs never occurs. These are referred as don't cares conditions. For each such condition, the letter D is entered into the corresponding square of the map. In doing the groupings and simplification, each D can be treated as a 1 or a 0, whichever leads to the simplest expression. Here in table 12.5, it shows the truth table for producing a 4-bit result that is 1 more than a 4-bit BCD input. The addition is modulo 10, thus 9 plus 1 equals 0. Also note that 6 of the input code produced don't care results because those are not valid BCD inputs. So BCD is binary coded decimal, just to remind you of what we're talking about there. So figure 12.12 shows the resulting Carnot map for each of the output variables. The D squares are used to achieve the best possible groupings. So D, remember, is don't care. For more than 4 variables, the Carnot map method becomes increasingly cumbersome. With 5 variables, 2 16 by 16 maps are needed, with 1 map considered to be on top of the other in 3 dimensions to achieve adjacency. 6 variables require the use of 4 16 by 16 tables in 4 dimensions. So that's something we can't visualize. An alternative approach is a tabular technique referred to as a Quinn-McCuskey method. The method is suitable for programming on a computer to give an automatic tool for producing minimized Boolean expressions. That is useful. So the first step is to construct a table in which each row corresponds to one of the product terms of the expression. The terms are grouped according to the number of complement variables. That is, we start with a term with no complements. If it exists, then all terms with 1 complement and so on. Table 12.6 shows the list for our example expression with horizontal lines used to indicate the grouping. For clarity, Each term is represented by a 1 for each uncomplemented variable and a 0 for each complemented variable. Thus, we group terms according to the number of ones they contain. The index column is simply the decimal equivalent and is useful in what follows. The next step is to find any pair of terms that differ in only one variable. That is, all pairs of terms that are the same except that one variable is 0 in one of the terms and 1 in the other. Because of the way in which we have grouped the terms, we can do this by starting with the first group and comparing each term of the first group with every term of the second group. Then compare each term of the second group with all of the terms in the third group, and so on. Whenever a match is found, place a check next to the terms, combine the pair by eliminating the variables that differ in the two terms, and add that to a new list. This process continues until the entire original table has been examined. The new table is organized into groups as indicated in the same fashion as the first table. The second table is then processed in the same manner as the first. That is, terms that differ in only one variable are checked, and a new term produced for a third table. In this example, the third table that is produced contains only the terms BD. In general, the process would proceed through successive tables until a table with no matches was produced. In this case, this has involved 3 tables. Once a process just described is completed, we have eliminated many of the possible terms of the expression. Those terms have not been eliminated and used to construct a table, construct a matrix, as illustrated in table 12.7. That's what we're showing here. Each row of the matrix corresponds to one of the terms that have not been eliminated, that is, has no check. In any of the tables used so far, each column corresponds to one of the terms in the original expression. An X is placed at each intersection of the row and column such that the row elements is compatible, quote, compatible with the column elements. That is, the variable present in the row element have the same value as the variables present in the column elements. Next, circle each X that is alone in a column. Then place a square around each X in any row in which there is a circle X. And every column now has either a squared or a circled X. Then we are done, and those row elements whose X's have been marked constitute the minimal expression. In cases in which some columns have neither a circle nor a square, additional processing is required. Essentially, we keep adding row elements until all columns are covered. Okay, one more real-time change. I just updated this table. There was a C that was wayward down here in the corner, so I put it back up here so you can see it, and I made it a little bit larger. So after me pausing it for a second, this may look a little bit larger, but everything else is the same. Just trying to put that up there so you can see this consistently across the board there. Okay, moving on. Another consideration in the implementation of Boolean a Boolean function concerns the type of gates used. It is sometimes desirable to implement a Boolean function solely with NAND gates or solely with NOR gates. We've mentioned this a little bit previously. Now we're getting a chance to see it from a gate perspective. While this may not be the minimal gate implementation, it has the advantage of regularity, which can simplify the manufacturing process. So it's not only trying to think of the most straightforward manner for capturing a program, but also thinking of manufacturing. All right, well, let's move on to some other types of devices. Here we have a multiplexer. The multiplexer connects multiple inputs to a single output. At any time, one of the inputs is selected to be passed to the output. A general block diagram representation is shown in figure 1214. This represents a 4-to-1 multiplexer or mux. There are 4 input lines labeled D0, D1, D2, and D3. One of these lines is selected to provide the input signal. One of these lines is selected to provide the output signal F. To select one of the 4 possible inputs, a 2-bit selection code is needed, and this is implemented as 2 select lines labeled S1 and S2. So those are at the bottom. An example of a 4-to-1 multiplexer is defined by the truth table shown in table 12.8, which we're showing now. This is a simplified form of a truth table. Instead of showing all possible combinations of the input variables, it shows the output as data from lines D0, D1, D2, or D3. So it's a switch, basically. Figure 12.15 shows an implementation uses and, or, and not gates. S1 and S2 are connected to the AND gates in such a way that any of the combination of S1 and S2, 3 of the AND gates will be output 0. The 4th AND gate will output the value of the selected line, which is either 0 or 1. Thus, 3 of the inputs to the OR gate are always 0, and the output of the OR gate will be equal to the value of the selected input gate. Using this regular organization is easy to construct a multiplexer of size 8-to-1, 16-to-1, and so on. Multiplexers are used in digital circuits to control signal and data routing. An example is the loading of the program counter or PC. The value to be loaded into the program counter may come from one of several different sources. First, a binary counter, if the program counter or PC is to be incremented for the next instruction. Then there's the instruction register, if a branch instruction using a direct address has been executed. Plus, there's the output of the ALU if the branch instruction specifies the address using a displacement mode. These various inputs could be connected to the input lines of a multiplexer with the PC connected to the output line. The select lines determine which value is loaded into the PC. Because the PC contains multiple lines, multiple multiplexers are used, 1 per bit. Figure 1216, as we're showing here, illustrates this for a 16-bit addresses. A decoder is a combinational circuit with a number of output lines, only one of which is asserted at any time. Which output line is asserted depends on the pattern of input lines. In general, a decoder has inputs and 2 to the n outputs. Figure 1217 shows a decoder with 3 inputs and 8 outputs. And so this can be called a demux, while the other one we talked about before was called a mux. So those are some shorthand names if you find them useful. Decoders find many uses in digital computers. One example is address decoding. Suppose we wish to construct a 1 kilobyte memory using 4 256 times 8-bit RAM chips. And we want a single unified address space which can be broken down like what we're considering here in the illustration. So you can keep that in mind. Each chip requires 8 address lines, and these are supplied by the lower order 8 bits of the address. The higher order 2 bits of the 10-bit address are used to select one of the 4 RAM chips. For this purpose, a 2 to 4 decoder is used, whose output enables one of the 4 chips as shown in figure 1218, which we're showing here. With an additional input line, a decoder can be used as a demultiplexer or demux. The demultiplexer performs the inverse function of a multiplexer. It connects a single input to one of several outputs. This is shown in figure 1219, which we're showing here. As before, n inputs are decoded to produce a single one of 2 to the n outputs. All of the 2 to the n output lines are AND together, and a data line input with a data line input. Thus, the n inputs act as an address to select a particular output line, and the value on the data line, and the value of the data input line, which would be a 0, 1, is routed to the output line. The configuration in 12.19 can be viewed in another way. Change the labels on the new line from data inputs to enable. This allows for the control of the timing of the decoder. The decoder output appears only when the encoded input is present and the enable line has a value of 1. Well, let's reflect again on read-only memory. We've talked about this previously. Combinational circuits are often referred to as memoryless circuits because their output depends only on the current input and no history of prior inputs is retained. However, there is a sort of memory that is implemented with a combinational circuit, namely read-only memory. Recall that a ROM is a memory unit that performs only the read operation. This implies that the binary information stored in a ROM is permanent and was created during the fabrication process. Thus, a given input to the ROM, that is the address lines, always produce the same output, the data lines. Because the output are a function only of the present inputs, the ROM is in fact a combinational circuit. A ROM can be implemented with a decoder and a set of OR gates. As an example, consider the table 12.9. I tried to label it in such a way that maybe would make it clear where the 1s and 0s are, so keep that in mind. This can be viewed as a truth table with 4 inputs and 4 outputs. For each of the 16 possible output values, the corresponding set of values of the output is shown. Can also be viewed as defining the contents of a 64-bit ROM consisting of 16 words of 4 bits each. The 4 inputs specify an address and the 4 outputs specify the content of the location specified by the address. Figure 1220 shows how this memory could be implemented using a 4 to 16 decoder and 4 OR gates. As with the PLA, a regular organization is used and the interconnections are made to reflect the desired results. Figure 1220 that we're showing now shows how this memory could be implemented using a 4 to 16 decoder and 4 OR gates. As with the PLA, a regular organization is used and the interconnections are made to reflect the desired result. Binary addition differs from Boolean algebra in that the results include a carry term. However, addition can still be dealt with in Boolean terms. In table 1210A, we show the logic for adding 2 input bits to produce a 1-bit sum and a carry bit. This truth table could easily be implemented in digital logic. However, we are not interested in performing addition on just a simple pair of bits. Rather, we wish to add 2 n-bit numbers. This can be done by putting together a set of adders so that the carry from one adder is provided as an input to the next. For a multiple bit adder to work, each of the signed bit adders must have 3 inputs, including the carry from the next lower order adder. The revised truth table appears in table 1210B. And so we're seeing a single bit and then with a carryover. So we have those two differences. A 4-bit adder is depicted in figure 1221. That's what we're showing here now. And with this figure, figure 1222 is an implementation using and, or, and not gates. And so now you can be getting a little bit more insight into how we would do these more complicated implementations. Now we have a construction of a 32-bit adder using 8-bit adders. Thus, we have the necessary logic to implement a multiple bit adder, such as shown in figure 1223, which we are showing at the moment. Note that because the output from each adder depends on the carry from the previous adder, there is an increasing delay from the least significant to the most significant bit. Each single bit adder experiences a certain amount of gate delay, and this gate delay accumulates. For larger adders, the accumulated delay can become unacceptably high. The carry value could be determined without having to ripple through all the previous stages, then each single bit adder could function independently and delay would not accumulate. This can be achieved with the approach known as carry look-ahead. Figure 1223 shows how a 32-bit adder can be constructed out of 4 8-bit adders. In this case, the carry must ripple through the 4 8-bit adders, but this will be subsequently quicker than a ripple through 32 1-bit adders. So combinational circuits implement the essential functions of digital computers. However, except for the special case of ROM, they provide no memory or state information elements, also essential for the operation of a digital computer. For the latter purpose, a more complex form of digital circuit is needed, the sequential circuit. The circuit output of a sequential circuit depends not only on the current input, but also the past history of inputs. Another and generally more useful way to view it is that the current output of the sequential circuit depends on the current input and the current state of that circuit. So in this section, we will examine some simple but yet useful examples of sequential circuits. As will be seen, the sequential circuit makes use of combinational circuits. The simplest form of sequential circuit is a flip-flop. There are a variety of flip-flops, all of which share two principles. The flip-flop is a bistable device. It exists in one of two states, and in the absence of input remains in that state. Thus, the flip-flop can function as a 1-bit memory. The flip-flop has two outputs, which are always the complement of each other. Here's an illustration of a flip-flop, the SR latch. So figure 1224 shows a common configuration known as the SR flip-flop or SR latch. The circuit has two inputs, S, which is the set, and R, which is the reset, and two outputs, and consists of two NOR gates connected in a feedback arrangement. So the outputs feed back to the inputs, and that's part of how this actually makes it work. So figure 1225 shows the NOR SR latch timing diagram, just to get a chance to see how that would look. And there's a little bit of a delay that we're banking on that makes this logic possible. So the SR latch can be defined with a table similar to a truth table called a characteristic table, which shows the next state or states of the sequential circuit as a function of the current state and inputs. In the case of the SR latch, the state can be defined by the value of Q. Table 1212A shows the resulting characteristic table. Observe that the input S equals 1, R equals 1 are not allowed because these would produce an inconsistent output. The table can be expressed more compactly as shown in 1212B. An illustration of the behavior of the SR latch is shown in table 1212C. The output of the SR latch changes after a brief time delay in response to a change in the input. This is referred to as an asynchronous operation. More typically, events in the digital computer are synchronized to a clock pulse, so the changes occur only when a clock pulse occurs. Figure 1226, which we're showing here, shows this arrangement. This device is referred to as a clocked SR flip-flop. Note that the R and S inputs are passed to the NOR gate only during the clock pulse. One problem with SR flip-flops is that the condition of R equals 1, S equals 1 must be avoided. One way to do this is to allow just a single input. The D flip-flop accomplishes this, and so that's what we're showing here. So figure 1227 shows a gate implementation of the D flip-flop. By using an inverter, the non-clock input to the two AND gates are guaranteed to be the opposite of each other. The D flip-flop is sometimes referred to as a data flip-flop because it is in effect storage for one bit of data. The output of the D flip-flop is always equal to the most recent value applied to the input. Hence, it remembers and produces the last input. It is also referred to as a delayed flip-flop because if it delays a 0 or 1 applied to the input for a single clock pulse. Another useful flip-flop is a JK flip-flop. Like the SR flip-flop, it has two inputs. However, in this case, all possible combination of the input values are valid. Thus, figure 1228 shows a gate implementation of the JK flip-flop. Figure 1229 shows the characteristic table along with those for the SR and the D flip-flops. Note that the first three combinations are the same as for the SR flip-flop. With no input asserted, the output is stable. If the J input is asserted, the result is a set function causing the output to be 1. If only the K input is asserted, the result is a reset function causing the output to be 0. When both J and K are 1, the function performed is referred to as a toggle function. The output is reversed. Thus, if Q is 1 and 1 is applied to the J and K, then Q becomes 0. You can look over this in more detail if you want to verify the implementation of figure 12.28 and that it produces this characteristic function. A parallel register consists of a set of 1-bit memories that can be read or written simultaneously. It is used to store data. The registers that we have discussed throughout this book are parallel registers. The 8-bit register of figure 1230 illustrates the operation of a parallel register using D flip-flops. The control signal labeled load controls writing into the register from signal lines D11 through D18. These lines might be the output of multiplexers so that data from a variety of sources can be loaded into the register. A shift register accepts and/or transfers information serially. Consider, for example, figure 1231 that we're showing here, which shows a 5-bit shift register constructed from clock D flops. Data are input only to the leftmost flip-flop. With each clock pulse, data are shifted to the right 1 position, and the rightmost bit is transferred out. Shift registers can be used to interface to serial I/O devices. In addition, they can be used with the arithmetic logic unit to perform logical shifts and rotate functions. In this latter capacity, they need to be equipped with parallel read/write circuitry as well as serial. Another useful category of sequential circuit is the counter. A counter is a register whose value is easily incremented by 1, module the capacity of the register. That is, after the maximum value is achieved, the next increment sets the counter value to 0. Thus, a register makes up a n flip-flops can count up to 2 to the n minus 1. An example of a counter in the CPU is the program counter. Counters can be designated as asynchronous or synchronous depending on the way in which they operate. Asynchronous counters are relatively slow because the output of one flip-flop triggers a change in the status of the next flip-flop. In synchronous counters, all the flip-flops change states at the same time. Because the latter type is much faster, it is a kind used in CPUs. However, it is useful to begin the discussion with a description of an asynchronous counter. Okay, let's continue on with the design of a synchronous counter. So an asynchronous counter is also referred to as a ripple counter because the change that occurs to increment the counter starts at one end and ripples through to the other end. The ripple counter has the disadvantage of the delay involved in changing values, which is proportional to the length of the counter. To overcome this disadvantage, CPUs make use of asynchronous counters in which all of the flip-flops of the counters change in the same time, which we mentioned. In this subsection, we present a design for a 3-bit synchronous counter. In doing so, we illustrate some basic concepts in the design of a synchronous circuit. For a 3-bit counter, 3 flip-flops will be needed. Let us use JK flip-flops. Label the uncomplemented output of the 3 flip-flops A, B, and C, respectively, with C representing the least significant bit. The first step is to construct a truth table that relates the JK input and outputs to allow us to design the overall circuit. Such a truth table is shown in figure 1233A, which we're showing. The first 3 columns show the possible combination of the outputs A, B, and C. They are listed in the order they will appear as the counter is incremented. Each row lists the circuit value of A, B, and C and the inputs to the 3 flip-flops that will be required to reach the next value of C, B, and A. Well, let's consider more the figure 1233A. Consider the first row. We want the value of A to remain 0, the value of B to remain 0, and the value of C to go from 0 to 1 with the next application of the clock pulse. The excitation table shows that to maintain an output of 0, we must have inputs of J equals 0 and don't care for K to effect a transition from 0 to 1. The inputs must be J equals 1 and K equals D. These values are shown in the first row of the table. By similar reasoning, the remainder of the table can be filled in. Having constructed the truth table of figure 1233A, we see that the table shows the required values of all the J and K inputs as functions of the current values of C, B, and A. With the aid of the Carnot maps, we can develop the Boolean expression for these 6 functions. This is shown in part B of the figure. For example, the Carnot map for the variable JA, the J input to the flip-flop that produces the A output yields the expression JA equals BC. When all 6 expressions are derived, it is a straightforward manner to determine the actual circuit as is shown in part C of the figure. So keep that in mind, and we'll continue on. At the level of integration provided by integrated circuits increases, other considerations apply. Early integrated circuits using small-scale circuits, SSI, provided from 1 to 10 gates on a chip. Each gate is treated independently in the building block approach described so far. To construct a logic function, a number of these chips are laid out on a printed circuit board and the appropriate pin interconnections are made. Increasing levels of integration made it possible to put more gates on a chip and to make gate interconnections on the chip as well. This yields the advantages of a decreased cost, decreased size, and decreased speed. Because on-chip delay are of shorter duration than off-chip delays. A design problem arises, however. For each particular logic function or set of functions, the layout of gates and interconnections on the chip must be designed. The cost and time involved in such custom chips design is high. Thus, it becomes attracted to develop a general purpose chip that can be readily adapted to specific purposes. This is the intent of the programmable logic device, or PLD. There are a number of different types of TLDs in commercial use. Table 1213, which I'm showing here, lists some of these terms and defines some of the most important types. In this section, we will look at one of the simplest such devices, the programmable logic array, or PLA, and then introduce perhaps the most important and widely used type of PLD, the field programmable gate array, or FPGA. So first, talk about the PLA. The PLA is based on the fact that any Boolean function that is truth table can be expressed in a number of products, so in a sum of products, a SOP form, as we have seen. The PLA consists of regular arrangements of NOT, and OR gates on a chip. Each chip input is passed through a NOT gate so that each input and its complement are available to each AND gate. And the output of each AND gate is available to each OR gate, and the output of each OR gate is a chip output. By making the appropriate connections, arbitrary SOP expressions can be implemented. Figure 1234A shows a PLA with 3 inputs, 8 gates, and 2 outputs. On the left is a programmable AND gate. The AND array is programmed by establishing a connection between any PLA input or its negation and any AND gate input by connecting the corresponding lines at their point of intersection. On the right is a programmable OR array, which involves connecting AND gates outputs to OR gate inputs. Most larger PLAs contain several hundred gates, 15 to 25 inputs, and 5 to 15 outputs. The connections from the input to the AND gates and from the AND gates to the OR gates are not specified until programming time. PLAs are manufactured in 2 different ways to allow programming that is making connections. In the first, every possible connection is made through a fuse at every intersection point. The undesired connections can then be later removed by blowing the fuses. This type of PLA is referred to a field programmable logic array. Alternatively, the proper connections can be made during chip fabrication by using an appropriate mask supplied by a particular interconnection pattern. In either case, a PLA provides a flexible, inexpensive way of implementing digital logic functions. So in the figure 1234B, it shows a program PLA that realizes 2 Boolean expressions. The PLA is an example of a single PLD or SPLD. The difficulty with increasing capacity of a strict SPLD architecture is that the structure of the programmable logic planes grows too quickly in size as the number of inputs is increased. The only feasible way to provide large capacity devices based on SPLD architecture is then to integrate the multiple SPLD onto a single chip and provide interconnections to programmably connect the SPLD blocks together. Many commercial PLD products exist on the market today, and this basic structure and are collectively referred to as complex PLDs. The most important type of CPLD is the FPGA. An FPGA consists of an array of uncommitted circuit elements called logic blocks and interconnect resources. An illustration of a typical FPGA architecture is shown in figure 1235. That's what we're showing here. The key components of the FPGA are logic blocks. The configurable logic blocks are where the computation of the circuits, of the user circuits, takes place. There's I/O blocks. The I/O blocks connect I/O pins to the circuits on the chips. And there's the interconnects. These are the signal paths available for establishing connections among I/O blocks and logic blocks. The logic block can be either a combinational circuit or a sequential circuit. In essence, the programming of a logic block is done by downloading the content of a truth table for a logic function. Figure 1236 that we're showing now shows an example of a simple logic block consisting of a D flip-flop, a 2-to-1 multiplexer, and a 16-bit lookup table. The lookup table is a memory consisting of 16 1-bit elements, so that 4 input lines are required to select one of these 16 bits. Larger logic blocks have larger lookup tables and multiple interconnect lookup tables. The combinational logic realized by the lookup table can be output directly or stored in the D flip-flops and output synchronously. A separate 1-bit memory controls the multiplexer to determine whether the output comes directly from the lookup table or from the flip-flop. By interconnecting numerous logic blocks, very complex logic functions can easily be implemented. All right, we covered a lot of ground, and hopefully with the explanation along with the figures, it's going to help to fill in some of the holes there. So we talked about Boolean algebra, its history and how it came about. We talked about the various types of gates that are used and the things that were going to be used in computers. We then talked about combinational circuits, how they can be implemented with Boolean functions. We talked about multiplexers, decoders. We had a reminder of read-only memory, and we talked about adders, half adders, and full adders. Then we talked about sequential circuits, flip-flops, registers, and counters, things that can store memory and provide several useful functions. And finally, we talked about programmable logic devices. First, we talked about the programmable logic array, or PLA, and the very useful, very adaptable field programmable gate array, the FPGA. All right, thank you very much. That's going to be it for this lecture.